Introduction. Both chemical kinetics and thermodynamics are branches in physical chemistry. But what is the difference between them? Chemical kinetics help us understand how fast reactions take place, while thermodynamics help us to know whether or not reactions occur. This chapter focuses on chemical kinetics. Chemical reactions, such as the metabolism of food to provide energy for human activities and the burning of fuel in vehicle engines, occur at different rates or speeds. Rates of chemical reactions range from fast, such as in fireworks, to slow, such as in rusting. Increasing the rate of a reaction is important to many processes, example, in the manufacture of drugs and fertilizers. In the collision theory of chemical kinetics, most reactions happen faster at a higher temperature. The rate of reaction, or the speed of reaction, is mostly affected by the reactant concentration and temperature. Chemical reactions generally occur when reactant molecules collide or knock into one another. According to collision theory, the reaction rate is directly proportional to the number of molecular collisions per second. Not all collisions between reactants succeed in bringing about a chemical reaction. Only those that are successful in changing reactants into products are known as effective collisions. Reactant particles, which are atoms, ions, or molecules, must be oriented or positioned appropriately to favor reaction. Collisions that do not result in a chemical reaction are called ineffective collisions. For example, the chemical equation shows the reaction of chlorine atom Cl with nitrosyl chloride molecule NaCl to give chlorine molecule Cl2 and nitric oxide molecule NO. In order for this to happen, chlorine atom Cl and nitrosyl chloride NaCl must be oriented correctly just before collision. That is, the Cl of NaCl molecule must be facing the Cl atom. When they smash into each other, the old bond between Cl and N in NaCl can break, and a new bond between the Cl atoms can be made to form Cl2 molecule. Nitric oxide is formed after Cl leaves NaCl. If the reactants are incorrectly oriented, such as when the oxygen of NaCl is facing the chlorine atom, no reaction occurs after collision. The two reactants merely bounce off each other. The potential energy, or Pe, is the energy stored within the bonds of the reactants, as well as the energy among or between the reactant particles, while the kinetic energy, or Ke, is the energy associated with moving particles. In a chemical reaction, energy is converted from potential energy to kinetic energy. Even when correctly oriented particles collide, a chemical reaction may not happen. For reaction to occur, the kinetic energy must also be enough to break the bonds within reactants. This amount of energy is called activation energy, EA, which is the minimum amount of energy required to start a chemical reaction. If there is enough Ke, old bonds will break and new bonds will form. Then one or more products will form. Conversely, if the reactants have low Ke and knock into one another sluggishly, reactant bonds stay intact and reaction will not proceed. In an effective collision, particles form an activated complex, also called a transition state. This species is the highest energy species in the reaction. It is not stable and so short-lived that it has never been isolated. In this energy profile diagram, the activation energy EA is shown as the difference in energy between the reactants and the activated complex. Does this energy profile diagram show an exothermic or endothermic reaction? It is an exothermic reaction as the potential energy of the products is lower than the potential energy of the reactants. Temperature is the scale used to measure energy of a substance. In any sample of a substance at a particular temperature, The individual particles in the sample have different KEs. Some particles move more slowly while some more quickly. Only a proportion have relatively high Ke that is equal to or more than activation energy, EA. In this diagram, the blue shaded region under the curve represents the proportion of particles that have Kes that are greater than or equal to EA, meaning that they are energetic enough to undergo effective collisions provided the other criterion, correct orientation, is met.